2 is the answer to that. Thank you, Emily. Adam Tashner, number 2 is. All right, last one goes to Noah. So close. 10 square roots of 2. Why is it not the other way around? And that's not what this is it? Yeah. So ultimately what we do, just to explain the process once again, we use something called the product property for radicals. We're going to do the product property again today, just with weirder indices is what they're called, roots. We're going to use the product property. The question we ask ourselves in this case, we ask ourselves, what is the largest perfect square factor that divides evenly into 200? And that's 100. Some of you may have even picked 25. That's not the largest perfect square factor, though. If you pick 25 times 8, you would have to square root the 8 again. Use your product property on that. So you could pick any perfect square factor, but you create yourself a little bit more work if you don't pick the largest perfect square factor. So again, just to remind you, no calculators for this particular lesson. I see most of you already put them, at least closed them up. This you're going to use your colored paper for. So the largest perfect square you have colored in that'll divide into 200 is 100. You square root the 100, it's 10. 10 root 2 is your answer there. So good. All right, and then the first 5 perfect cubes. Caitlin. You skipped 1. 1 is perfect cube. You should have colored in 1 lots of times. So 1 is usually the first one we think of. But all the other numbers you listed were perfect cubes, so that's great. I really like that you went with perfect cubes. A couple people that I called on today throughout the course of my day started listing perfect squares. So they're like 1, 4, 9, 16. I was like, whoa, cubes. And there's a difference. We're going to, be more, we're going to discern that a little bit more clearly today for sure. Questions about the warm-up? Your prior knowledge is in place? We're good? All right. So we start off today. Ultimately, the goal, eyes on the prize, is to be able to simplify radical expressions when there's an integer underneath your radical. But before we get into that, we have to talk about the parts or the anatomy of a radical expression. So this whole big thing right here is what we call a radical expression. And it's called a radical expression because of the appearance of this radical, or some people call this the root symbol. It's very common to, take the square root of 4 or the square root of 16, just like you did in the warm-up. Like I said, those are very common problems, square root problems. You folks know that. What I'm drawing out right now is that you folks know that there's usually some number under there, some combination of numbers and letters. Whatever's underneath that radical is what we define as the radicand. So everything underneath the radical is what we call the radicand. And then in the warm-up, there was no number here, but we kind of moved past that in this chapter because it's all about different types of radicals. So really, you could have any integer greater than 1 up in that box right there. So I abbreviate that number with the letter n. And that number that's kind of nestled very nicely in this root bar here is what we call the index. Sometimes there's no number there at all, like in your warm-up. And in this case, if there is no number, in other words, if the index is not written, it's safe to assume that the value of the index is actually a 2, in which case you're taking a square root. like in your warm-up. Square root of 4. We didn't write the index. The index was 2. So let's see if you understand the anatomy of a radical. What you're going to do right now is take a quick moment, and you'll see a list of radical expressions here off to the right. Your mission is to determine the index and radicand of each of those radical expressions. So next to each one, I need you to put the index and the radicand. Ready, set, go. I'm pleased because I'm seeing, as I walk around, I'm seeing two things. One, that you folks get the idea that if there's no number tucked into the radical, then that does indeed mean that the index is actually 2. Furthermore, I'm glad to see that you're all understanding that the radicand is everything underneath the root symbol. So now we're ready to turn the page, and let's develop some vocabulary out of this. You actually get a chance for a change to define these terms, okay? Here's how this is going to go ahead and work. You're going to take a nice quiet moment to write some mathematically accurate definitions for the terms that are listed in your notes. Now, based on what you write, I would do this in pencil because you may have to add a little bit to your definition or change something. So I would do this in pencil just so that you have the flexibility to erase if you need to, because in a few moments, I'm going to go ahead and go over or show you what these definitions should look like. But it's not often I give you the opportunity to try to write for yourself mathematically accurate definitions, and this is something that you need to start to be able to do for yourself. So go ahead, take a quiet moment now, and you're going to define those terms for me. And you can do in your own words as long as they're mathematically accurate, which means they encompass all the different cases that we could possibly have for that one term. Spoiler alert, you guys always have the advantage of me having taught this class twice before you come in. The first definition is the one that students most had to fix up. So there's going to be some pieces that you'll probably need to add to that definition. But the other ones I think you might be able to do. So go ahead and give it a try. So here comes a couple more. Bam. So you want to take a moment to check. I have a feeling the last 4 probably went pretty smoothly, but that first one, like I said, has been elusive most of my day. Okay, so with that, today's topic, now that we've sort of nashed out the parts of a radical, our overall mission is to be able to simplify radical expressions when there's just integers in your radicand. Did you like that sentence that came out of my mouth? I just used like 4 of our vocabulary words on that purple sheet there. But yeah, we want to be able to simplify radical expressions when there's an integer underneath your radicand, right? That's what we're doing today in class. Tomorrow, we throw variables into the mix. Overall, when we are asked to simplify, when you see that word appear on the paper, you must think of these 3 properties that are up on the board behind me. So we're going to start with the ones that I think you already have a pretty good grasp on. For instance, this one in the middle, just by evidence of what Noah was talking about in the warm-up, I know that you have a pretty good understanding of the product property. I know that you know that when there's multiplication in our radical problem, you could glue the 2 radicals together around that product, or you could break them apart. For instance, we have the square root of 10 times the square root of 5. I know that you know that that is the same as the square root of 10 times 5, or the square root of 50. I also know that you know square root of 50 is not a legit answer. That is not in simplified radical form. So we could also use the product property again to break that radical apart, to simplify it. So the square root of 50, the largest perfect square factor that goes into 50, is 25, yes. And it breaks down to 25 times 2. So we get 5 root 2 when that is all said and done. I think that's a property most of you are pretty comfortable with. But does anybody have any questions about it? The next property in my experience that usually is pretty well absorbed at this point in your math career is the quotient property for radicals, and that's this bottom one here. You folks know that you can break a radical apart or glue it back together whenever there's a fraction bar in that problem, right? So our quotient property for radicals. In other words, you see that square root of 2 over 25? We can actually break that apart to be the square root of 2 over the square root of 25, which is the same as the square root of 2 over 5. All done. You might recall there's no radical in the bottom of that fraction, so we don't need to rationalize the denominator. We'll take care of rationalizing a little later on again in the chapter. And the last property we have that we have to think about when it says simplify, we have this power property for radicals. And when you look at this property, your eyes should go to that M that's there, this one right here. Do you see how it could be inside the radical? It's part of the radicand. Or it could be outside and we still produce an equivalent expression. That's true. Those are true. So I can show you that with this guy. You all know the cube root of 64, right? What is it? 4, yeah. But what I ask you to do is think about it in maybe a slightly different way. I know that 64 is the same as, it's also a perfect square. It's one of those numbers you would have colored twice in your homework last night. 64 is also 8 squared. So I could actually think about the cube root of 64 as the cube root of 8 squared, which is the same as the cube root of 8 all squared. And we know the cube root of 8 too from the last chapter when we had to factor our sums and differences of cubes. Cube root of 8 is 2. 2 squared is 4. Bam, I still got the same answer. So this property holds water for us, for sure. So when the directions say simplify, you need to think of the power, product, and quotient properties for radicals. Questions about those properties? What's up, Alec? Yes. Are you looking here? Oh, right there. Okay, when you say they, are you talking about the radicand, the index? The index, good. That's what I thought you were talking about. We want to use our words carefully in math class, avoid pronoun usage as much as possible. In order to apply these properties, the indices must be the same. So do you see how it's the nth root, the nth root, the nth root, the nth root? That n, that number has to be the same. Or else we have to go through a different process that we will learn how to do later on in the chapter. We just can't use these properties. So right now my eyeballs go to the product. So I think product property for that looks like a little smiley face. This is going to be the same as the cube root of 4 times 2, which is the same as the cube root of 8, which is 2. So I see the product there, so I use the product property. For part B, I'm going to use the power property. I know that squared can go inside or outside the parentheses. So I'm going to square root 5 and then square it. That's the same as the square root of 25, which ultimately yields 5 as a simplified answer. For part C, I see the product again. So I am going to use my product property on that guy there. This is the same as the cube root of 5 times 25, which is the cube root of 125. And then you know that that's a perfect cube. That also evaluates to 5. And then I see a quotient in part D. So I would use the quotient property. Ooh. You have A through B on independent practice 1 is 5. Alrighty. We will continue this section tomorrow. To be continued.